All right, welcome. Today, we're going to pull back the curtain on the invisible, super high-speed brain that makes your phone's connection actually work. It's called the MAC layer, and you can think of it as the real-time decision engine right at the heart of LTE. Okay, let's dive in.
Really think about it for a second. You're in a stadium with thousands of other people, right? And everyone is trying to post photos, stream videos, send messages, all at the exact same time. How on earth does the network handle that kind of chaos without just completely grinding to a halt? Well, the answer is in the MAC layer we're talking about today. You know, the best way to picture the MAC layer is to think of it as the network's air traffic controller. It sits right in the middle of everything. So you've got the RLC layer above it. That's kind of like the logistics team planning what cargo needs to fly. Then below it, you've got the physical layer, or the Fizzy, and that's the pilot who actually flies the plane. The MAC layer, that's the controller in the tower, making all the critical split-second decisions about who gets to take off and when.
So here's our flight plan. First, we're going to define what that traffic controller's mission really is. Then we'll peek inside the decision engine itself. We'll see how it pulls off this incredible balancing act between fairness and speed. We'll get into the rules of how data flows. And finally, we'll uncover the surprising reason your phone always has to wait its turn to send data.
Okay, first up, let's nail down exactly what this air traffic controller is responsible for. Its mission is, and this is no exaggeration, probably the most critical real-time job in the entire network. This quote just says it all, doesn't it? The physical layer, the PHY, it's pure muscle. It just does what it's told. It handles the radio waves, the modulation, the raw sending of bits. But it doesn't think. All the intelligence, every single decision comes from the MAC layer.
And what's so amazing is the sheer scope of these decisions. The MAC decides who gets to talk, when they can talk, which specific radio resources or resource blocks they get to use, and how they should pack their data for the best efficiency. This, right here, is the most important takeaway. The MAC layer is where abstract requests, like I want to watch a video, get translated into actual physical resources on the airwaves.
So how does this decision engine actually pull this off? Let's zoom right into its core, the scheduler, and talk about the absolutely mind-bending speed it has to operate at.
1 millisecond. That's 1/1000th of a second. It is the entire time budget the MAC scheduler gets to make a complete set of decisions for every single user in the cell. It's just this constant, relentless, high-speed loop. If it misses a single deadline, the whole cell could come crashing down.
Now, to make these crazy fast decisions, the scheduler needs good information, and it gets constant reports from every phone. The two big ones are the Channel Quality Indicator, or CQI, and the Buffer Status Report, or BSR. So, back to our analogy, the CQI is like the weather report. It tells the controller how clear the skies are for a particular phone. And the BSR? That tells the controller how much data or how many planes are sitting there waiting in line at the gate.
All right, so the controller has all its inputs. It knows the weather, it knows who's waiting. But with maybe hundreds of phones all screaming for attention, how does it decide who gets to go next? This is where the scheduling algorithms come in, and it's a really fascinating balancing act. You've basically got three main flavors. First, there's round robin. Super simple. Everyone gets a turn. It's totally fair, but it's also incredibly inefficient because it completely ignores who has a good signal. On the complete opposite end, you have max CQI. This one is ruthless. It only ever serves the user with the absolute best connection to maximize speed. The problem, users at the edge of the cell basically get starved of service. And that's why the entire industry landed on the third option, proportional fare. It's this genius compromise. It prioritizes users who have a good signal right now, but it also considers how long they've been waiting. It perfectly balances fairness with speed, and it's the standard in pretty much every real-world network out there.
So we know how the MAC decides. Now let's look at how it actually organizes all the data it's juggling. It doesn't see video or email. No, it sees things in a much more structured way, using something called channels.
First up, you have logical channels. These basically define what the data is. Just think of them as categories for the cargo. Is this critical system information that everybody in the cell needs to hear? Is it a specific control signal for just one user? Or is it just regular user data? You know, the payload. And you can see these categories broken down right here. You've got your control channels for things like system info and paging, and then you've got traffic channels for the actual user data, the stuff you and I really care about. And believe me, each of these carries its own level of priority.
So, if logical channels are the what, then transport channels are the how.
These are the actual pipes or runways that the MAC layer uses to move the data. For instance, there's a big shared runway for data coming down, the DLSCH, and another shared runway for data going up, the ULSCH. Almost all our data travels on these.
And this slide, right here, shows the most important part of this whole channel concept. The scheduler, it doesn't actually care about those logical categories. Its entire world, the only thing it is actually scheduling are the transport channels. It takes data from all those different logical channels and mashes them together, or multiplexes them onto these shared runways every single millisecond.
We're at our final core concept, and it's a really important one. It explains a ton about network lag or latency. It's all about the fundamental difference between receiving data and sending it.
See, when data is coming down to your phone, it's basically immediate. The network tower is the air traffic controller, and it controls everything, so it can decide to send and then send in the very same instant. But for the uplink, when your phone wants to send something, it's a whole different ballgame. Your phone can't just transmit whenever it feels like it. That would be total chaos. It has to ask for permission first.
This whole process follows what's known as the N+4 rule. So at time N, your phone sends up that buffer status report saying, hey, I've got data to send. The network needs a little time to process this and run its scheduler. And then finally, at time N+4, a full 4 milliseconds later, your phone gets a grant, giving it permission and telling it exactly which resources to use. This built-in minimum 4ms delay loop is a huge reason why the total round-trip time in LTE is usually around 8 to 10 milliseconds.
So, let's bring it all home with a quick engineer's cheat sheet. We learned the MAC operates on that insane 1 millisecond cycle time. It uses a proportional fair algorithm to balance that constant tension between speed and fairness. It has to deal with that fundamental N+4 uplink delay. It makes sure everything is reliable using a system called HARQ for super-fast retransmissions, and it speaks its own special command language called DCI to tell all the phones what to do.
Look, if you remember just one thing from all of this, make it this sentence. This is the killer definition that sums it all up. The LTE MAC is a real-time scheduler that multiplexes logical channels, controls reliability, and translates quality of service demands into actual time and frequency resources every single millisecond.
So, the next time you're in that crowded stadium and you pull up a video without a problem, just take a second. Can you picture that invisible air traffic controller, that incredible real-time decision engine making 1,000 complex judgments every single second just to make your connection feel seamless? It's an absolutely incredible piece of engineering happening right there in the palm of your hand. Thanks for joining me.